Welcome back to Talk Tensors. Today, we're diving into P-TAME.
P-TAME.
This is Explain Any Image Classifier with Trained Perturbations.
Very cool paper.
This one was sent in, actually.
Nice.
So, we always love it when you send these in. It helps us figure out what to actually talk about.
Absolutely.
And this one kind of hits on something that is, I think, really, really interesting for a lot of people, which is how AI makes sense of images.
Yeah, and I think that it's interesting because deep neural networks, DNNs, have become incredibly powerful at image recognition, but they've traditionally been black boxes.
Right.
We don't really know why they arrive at their conclusions. And that can be a problem, especially when you start thinking about applications where we need to be able to trust the AI's decisions, like in healthcare or self-driving cars.
Yeah, like if a doctor's using an AI system to, help diagnose patients or something like that.
Exactly.
We really want to be able to see, like, okay, why did it highlight this part of the X-ray or the CT scan, whatever.
Right.
So what is this P-TAME?
So P-TAME stands for Perturbation-based Trainable Attention Mechanism for Explanations.
Okay.
And it's a really clever approach to understanding how AI models make decisions about images.
Okay, so how does it work?
So imagine, like, you're a detective, right? You're investigating a case.
Okay.
And you're trying to understand why a suspect did something.
Right.
Instead of trying to, like, read the suspect's mind directly, you gather clues and evidence, right? And you use those to piece together their motives. That's kind of what P-TAME does.
Okay.
It doesn't try to, like, dissect the AI model's brain or anything like that.
Okay.
Instead, it focuses on the evidence, the image itself,
Okay.
and figures out which parts of the image are most important for the AI's decision.
Oh, interesting. So it's like looking at the crime scene photos, but for AI.
Exactly. And it does this by using an auxiliary classifier, which is a pre-trained neural network that's really good at picking out features in images, things like edges, textures, shapes.
Oh.
And these features become our clues, right? So it's like P-TAME has a partner, a specialist in image feature detection,
Okay.
that helps it understand what the main AI model might be focusing on.
And this is where things start to get really interesting, right? Because it's not just about identifying these features.
Yeah.
It's about understanding how they relate to the AI's decision-making process.
Exactly.
Right.
So P-TAME uses these features to create what's called an attention map, which basically highlights the regions of the image that are most likely influencing the AI's decision.
So it's like a heat map showing where the AI is paying attention.
Yeah, think of it like a spotlight
Okay.
shining on the most important clues in our detective's case.
I like that. Yeah, the spotlight analogy. That's a good word.
Right, it helps you kind of visualize what's happening.
Yeah, that makes it a little bit more concrete.
So it's not just randomly highlighting pixels, it's actually using these extracted features to pinpoint the parts of the image that the AI is really paying attention to.
Okay, so we have these features. We have this attention map. How does P-TAME actually know if it's highlighting the right things? How does it learn?
That's the really clever part. So during training, P-TAME plays this game of hide and seek with the AI.
Oh.
It starts masking parts of the image based on this attention map and sees how the AI's confidence in its classification changes.
Okay.
So if masking a certain area makes the AI less sure about its answer, then we know that area was probably a key clue.
So P-TAME's like, hey, AI, I'm covering up this part of the image. Do you still think it's a cat? Oh, you're less sure now. I guess that part was important after all.
Exactly. It's like a scientist testing a hypothesis, right?
What?
By systematically masking different parts of the image, P-TAME learns which features are truly driving the AI's decision-making.
So it's not just about explaining, it's about making sure the explanation is actually valid.
Precisely.
Right.
And it's a really powerful way to ensure that we're not just highlighting random things, that the explanation actually makes sense.
I mean, this is already like super cool and we're just scratching the surface here. But before we dive too deep into how P-TAME performs, I think it's important to take a step back and look at the bigger picture of explainable AI, right? This quest for understanding AI's reasoning, it's not exactly new, right?
Yeah, you're absolutely right. The desire to understand AI's reasoning has been around for a while, and there have been a lot of different approaches over the years.
So like, what were some of those early attempts? What were their strengths and weaknesses?
Well, one of the early approaches was gradient-based methods, and these try to trace back the AI's decision to the specific pixels that influenced it the most. It's like trying to figure out which parts of a photograph are most in focus.
Okay, that makes sense.
But, these methods can be very sensitive to noise, picking up on insignificant details that don't actually matter for the decision. They can also be tricky to adapt to different AI architectures.
So not exactly plug and play.
Right. Not as flexible as we'd like.
What other approaches were out there?
Another category is perturbation-based methods, and like P-TAME, they involve altering the input image. But instead of systematically masking regions like P-TAME does, these methods often rely on random masking. It's kind of like trying to understand a painting by randomly throwing paint at it and seeing what sticks.
Okay, so that sounds a bit chaotic.
It can be.
Did it work? Like, was that approach at least like more flexible compared to the gradient-based methods?
Yeah, it was definitely more adaptable to different AI architectures, but it was often very computationally expensive. You might have to run the AI thousands of times with different random masks just to get a good explanation.
So it's like brute forcing an explanation.
Yeah, pretty much
Not very elegant.
not very efficient.
Yeah.
And it takes a lot of computing power.
Okay, so we've got gradient-based methods that are very specific and sensitive.
Right.
And then we've got these perturbation-based methods that are very computationally heavy.
Yeah.
It seems like the field was really ready for something that could combine like the best of both worlds.
Exactly. And P-TAME takes inspiration from both of these approaches and combines them in a really clever way.
Okay.
It uses an attention mechanism, like some other techniques like TAME and T-TAME,
Okay.
but it combines it with this systematic perturbation technique that we talked about earlier, and that allows it to be both efficient and model agnostic.
Okay. So how did they actually test it?
To test how well P-TAME works, they used a bunch of different deep neural network architectures,
Okay.
like VGT16, ResNet50, and VTB16, just to make sure that it wasn't just working on one specific type of AI model.
So they really put it through its paces.
Yeah, they wanted to see if it could generalize across different approaches to image recognition.
And how did it do? Did it manage to impress?
The results were really good. P-TAME did as well as, or even better than other state-of-the-art methods, but it was also more efficient and adaptable.
So it wasn't just explaining, it was explaining well.
Exactly. They used quantitative metrics, like increasing confidence, to measure how much more certain the AI became about its classification after P-TAME highlighted the relevant regions.
Oh, that's cool. So you can actually measure how much more confident the AI is.
Yeah, it's a way to quantify the quality of the explanations.
Okay. But did the explanations like actually make sense? Like, did they look right to a human?
Yeah, they also visually inspected the saliency maps generated by P-TAME. And those are basically heat maps that show you which parts of the image the AI is focusing on. And they found that these maps were accurate and easy to interpret, even for really complex images.
So you could show these maps to a human and be like, hey, does this make sense? And they'd be like, yeah, I see what the AI is doing there.
Exactly. And that's a huge step forward in making AI more transparent.
Absolutely.
Because now we can not only see what the AI is doing, but we can also understand why.
And the fact that it can generate these explanations quickly in a single forward pass, that's pretty impressive too, right?
Yeah, it means that P-TAME can be used in real-time applications. Okay.
Where speed is really important, like self-driving cars or medical diagnosis.
So before we get into our novel notions segment, I do want to ask about one more thing. The paper talks about an ablation study, right?
Yeah.
What is that and why is it important?
So an ablation study is basically where you remove or alter different parts of a system
Okay.
to see how it affects performance.
Yeah.
It's like, what happens if we take out this part of P-TAME? Will it still work as well?
Right.
Will it become faster, slower?
Okay.
And what they found is that using a simpler auxiliary classifier might make things a bit faster,
Okay.
but it often comes at the cost of accuracy.
So there's a trade-off there.
Exactly. Like with most things in life.
Yeah. No free lunch.
Right.
So overall, it seems like P-TAME strikes a pretty good balance between accuracy, efficiency, and adaptability.
Yeah. It's a big step forward for explainable AI.
Okay. So we've covered a lot of ground already, from understanding why we need explainable AI to exploring how P-TAME works and how it compares to other methods.
I think it's time to shift gears a little bit and get into some of the what-ifs of this research.
Absolutely. Let's get speculative.
Okay, are you ready for novel notions?
Always. Let's push the boundaries and see where this research could lead us.
Awesome. Let's do it.
Welcome back to Talk Tensors. In part one, we kind of set the stage, right? We talked about why explainable AI is important and some of the history that led to this paper.
Right, kind of the background, the motivation for this whole area of research.
Yeah, and now I think we're ready to really dive into the nitty-gritty of P-TAME.
Okay, I'm ready to get a little more technical.
Yeah.
Let's pop the hood and see what's going on under there.
All right, so at its heart, P-TAME really has two main stages. training and inference.
Okay.
And during training, the goal is to basically teach the attention mechanism to highlight the right parts of the image.
The parts that actually matter for the AI's decision.
Exactly. And this involves kind of a clever back and forth between the auxiliary classifier, the attention mechanism, and that perturbation technique we talked about earlier.
All right, the hide-and-seek game.
Yeah. So step by step, let's break it down.
Right.
First, we've got the auxiliary classifier, which is like our feature detective.
Right.
It takes the input image and generates a set of feature maps, which are kind of like different layers of understanding, from simple edges and textures to more complex patterns and shapes.
So it's like dissecting the image, extracting all these potential clues.
Exactly. And then these feature maps get fed into the attention mechanism, which is like a spotlight that learns to focus on the most important parts of the image based on those features.
Okay, so we've got the detective's toolkit, the extracted features, and then we use the attention mechanism to kind of create a heat map of the areas of interest.
Right. And this is where the training gets really interesting, because P-TAME uses the attention map to guide the masking process during training.
Oh, right, the hide-and-seek part.
Yeah, so it's like
Huh.
P-TAME is saying, okay, I think this region is important. Let's cover it up and see if the AI still gets the answer right.
And if the AI is less confident, then that masked area was probably important.
Exactly. And based on the AI's response, P-TAME can adjust the attention mechanism, making the explanations even more accurate.
So it's like a constant back and forth testing and refining.
Right. And to make sure that the attention mechanism doesn't just learn to create a completely opaque mask, hiding everything, P-TAME uses what are called loss functions during training.
Okay, so this is to prevent the attention mechanism from, like, cheating or taking shortcuts.
Yeah, basically, it's like setting boundaries, making sure the explanations are both accurate and meaningful.
So some loss functions encourage the attention mechanism to focus on small, specific areas, while others promote smooth, visually coherent explanations.
Exactly. It's a delicate balance, you know? You want the explanations to be true to how the AI is actually behaving, but also understandable to humans.
It's like trying to translate between two different languages.
Yeah, in a way.
So this training process, it sounds pretty complex.
It is, but it's this complexity that allows P-TAME to generate really insightful and trustworthy explanations.
Okay, so once the training is done, how does P-TAME actually explain a new image, one that it hasn't seen before?
So during inference, there's no masking or anything like that.
Okay.
The new image goes into both the main AI model and the auxiliary classifier.
Okay.
The auxiliary classifier extracts those feature maps,
Right, the clues.
and then those are passed through the train attention mechanism, which has already learned how to identify the important bits.
So it's like the detective has already done all the hard work and can now apply their knowledge to a new case.
Exactly.
Yeah.
And the attention mechanism combines those features to create the explanation map.
Highlighting the regions that probably influence the AI's decision.
Right.
And this all happens in a single step, right? That's why it's so efficient.
Exactly. That's one of the big advantages of P-TAME. It's designed to be practical and usable in real-world scenarios.
Okay, so were there any challenges that came up during, like, the development of P-TAME?
Yeah, definitely. I mean, one of the challenges was finding the right balance between those different loss functions during training.
Right, the trade-off between accuracy and interpretability.
Exactly. And to address that, they use something called Bayesian optimization.
Okay, and what is that?
It's a smart search algorithm that helped them find the best combination of those loss function weights.
So it's like an AI assistant helping them train P-TAME.
Kind of, yeah. And another challenge they mentioned was the potential for mismatch between the auxiliary classifier and the main AI model.
Okay, so how could that happen?
Well, using a pre-trained auxiliary classifier is really efficient, right?
Right.
But it might not always capture the specific features that the main AI model is relying on.
So it's like the detective's toolkit might be missing a crucial tool.
Exactly. And to address that, they suggest fine-tuning the auxiliary classifier, which basically means customizing it to match the main AI model.
So it's like giving the detective a chance to update their tools based on their experience.
Right. And that could lead to even more accurate explanations.
Okay, so it sounds like we've covered a lot of the technical details here.
Yeah, I think we've got a pretty good understanding of how P-TAME works now.
I'm ready for some more novel notions.
Okay, let's get into some more speculative territory and see what crazy ideas we can come up with.
Sounds good to me. Welcome back to Talk Tensors. We've really gotten into the weeds with P-TAME, haven't we? Explored how it works, all the technical stuff, even brainstormed some pretty wild future possibilities.
Yeah, definitely. It's been a fun deep dive, but I think it's time to step back and think about what all of this means for the real world, you know?
Right, like how can P-TAME actually be used to make a difference?
Exactly. And I think one of the most obvious areas is healthcare.
Yeah, I mean, healthcare is all about trust and transparency, right?
Absolutely. So imagine you're a doctor and you're using an AI system to analyze a patient's medical images, like x-rays or CT scans.
Bam.
And instead of just getting a prediction, like possible tumor detected, you also see a heat map generated by P-TAME, highlighting the specific areas the AI focused on.
Oh, wow. So it's like the AI is showing its work, basically.
Yeah. It's saying, hey, doc, I'm not just spitting out a random guess. Here's the evidence I'm using.
That would be huge for a doctor trying to make a diagnosis.
Absolutely. It allows them to combine their own expertise with what the AI is seeing.
Right.
And potentially lead to earlier, more accurate diagnoses.
And don't forget, P-TAME can also help us identify biases in AI, right?
That's right. And in healthcare, that could be literally life-saving.
Yeah, making sure the AI isn't making unfair or inaccurate judgments based on a patient's background or something.
Exactly. It's about making AI not just more transparent, but also more fair.
And that's especially important in healthcare, where those decisions have such high stakes.
Absolutely. And it goes beyond diagnosis, too. Think about personalized treatment planning.
Okay.
Imagine an AI system that can recommend a treatment plan, but also explain why that plan is the best option for a particular patient.
Oh, wow, that's powerful.
Right. It takes into account their medical history, their genetics, all of that.
It's like having an AI-powered medical consultant.
Yeah, exactly. Working alongside the doctor, providing personalized recommendations.
So we've talked about healthcare, but I'm sure there are tons of other fields where P-TAME could have a big impact.
Oh, absolutely. Another big one is autonomous driving.
Right, self-driving cars.
Yeah, as those become more common, understanding why the AI is making decisions is crucial for safety.
It's like, okay, the AI swerved to avoid something, but what was it? A pedestrian, a squirrel?
Exactly. And P-TAME could provide that insight. It could show us what the AI was focusing on, why it made certain maneuvers.
That's a game changer for building trust in self-driving cars.
Absolutely. And it's not just about self-driving cars either.
Okay.
Think about traffic management in cities, optimizing shipping routes, even air traffic control.
Right, AI is getting involved in all sorts of transportation and logistics.
And in all of these areas, explainability is crucial.
For safety, efficiency, all of that.
Exactly.
Okay, so we've got healthcare, transportation, what else?
Well, think about the economic implications. Explainable AI could lead to totally new industries.
Like what?
Well, imagine companies that specialize in AI auditing.
AI auditing.
Yeah, experts who analyze the explanations provided by AI systems.
Oh, interesting. To make sure they're fair, accurate, and not doing anything shady?
Exactly. It's like cybersecurity, but for AI.
Right. As AI gets more powerful, we need ways to keep it in check.
Absolutely. And as we talked about with our novel notions, explainability isn't just about understanding existing AI.
Right. It can also help us build better AI.
Exactly. More robust, less biased, more adaptable.
It's like using explainability as a blueprint for AI development.
I like that. A blueprint for building AI that's truly beneficial.
So what's the main takeaway here? What do you hope people will remember from this deep dive?
I hope people will remember that AI doesn't have to be a mystery.
Right.
We can build AI systems that are understandable, trustworthy, and ultimately help us make the world a better place.
And P-TAME is a huge step in that direction.
Absolutely. It shows us what's possible when we prioritize explainability.
Well said. So, on that note, we're going to wrap up this episode of Talk Tensors.
It's been a great discussion.
As always, the link to the full paper is in the show notes, so go check it out if you want to dive deeper.
Yeah, and let us know what you think.
Thanks for listening, and we'll see you next time.